Good morning, ladies and gentlemen. This is Ben Kieser with Applied Flow Technology. Happy May 1st, 2019. I hope that everyone is having a wonderful week. Want to thank you all for joining me in my webinar today. And before we jump into things, I want to make a quick announcement of something that we're all very, very excited about here at AFT. If you were to download the latest release of AFT Fathom, which can be found on this page right here, when you go to run Fathom the next time, you'll see a brand new little blurb that shows up in the startup window. That is this brand new feature right here, the automated network sizing module. The automated network sizing module is officially ready and able to be purchased and used in your calculations, and we're really excited about that. What the new automated network sizing module will do is it will automatically meet your design requirements by changing your pipe size for you while minimizing your life cycle cost or perhaps your piping weight. It's a very powerful capability that was available in AFT Mercury and AFT Titan for about 15-20 years, and we have just finished incorporating it into AFT Fathom as a brand new add-on module. So there will be no more AFT Mercury and AFT Titan. It's going to be the new Automated Network Sizing Module, ANS for short. It's available now for AFT Fathom, and it should be available very soon for AFT Arrow coming up in the next few weeks or so. Where can you find information about it? Well, if you go to the Fathom product page, then near the bottom here, if you scroll down to the add-on modules, you can find information about the automated network sizing module, as well as the extended time simulation module, which I'll be discussing today, and a couple others. And so if you were to go into the automated network sizing module, then it will take you to the page here where you would specify if you are a owner-operator or if you work with an EPC firm. The module is the same, but the information that is pertinent for how you would use the ANS module in each of the different situations is slightly different, just because there's different things that people care about depending on which side of the fence they're on. So if you chose one of these, it'll take you to the ANS page, and you can read all about the various capabilities and see some screenshots. You can contact us for more information. So definitely be sure to check out the ANS module when you have a chance. We'd be more than happy to provide a evaluation license for you if you'd like to give it a try. We also are doing a limited time promotion where if you purchase the ANS module within the next 6 months, you can purchase it for half off the regular price. And contact us for our regular prices, and we'll give you 50% off for it. If you are outside the United States, you can contact your channel partner, and they'll be glad to assist you. All right. So what we're going to be talking about today is to stop using spreadsheets for your flow calculations. I have the opportunity where I get to travel a lot and do a lot of different lunch and learns, and I also get to do training seminars and company visits, and a lot of times I'll run into companies that when they're trying to do a transient analysis, they'll show me this big, massively long spreadsheet where they've tried to program in all the various transient calculations, and it's just a nightmare. And you know, there's also a lot of people out there that will still rather use their spreadsheet rather than other software tools, and it just opens up the door for so many mistakes to happen. And so I'm going to talk a little bit about that today. So here's what I have on the agenda for this morning. By the way, my presentation is available to you in the live webinar right now. So if you're listening in, you should be able to download the PDF of my webinar. The webinar is also being recorded, so that way if you want to listen in again later or you want to send it around to your colleagues, you can. And if you're listening to the recorded version, feel free to contact me personally, Ben Keiser at AFT.com. That's BenKeiser at AFT.com. I'll be happy to send you my presentation. So here's what we're talking about today. We're going to take a quick trip down memory lane. We'll talk about the flow calculations of the past, flow calculations of the present and future, and steady state is really easy, but are things ever really steady state? So as I was preparing for this webinar, it has a, transient aspect to it, and I kind of wanted to make it a little bit fun. So what were you doing 10 years ago? As I look back, I can't believe how fast the last 10 years have gone by. And what was I doing 10 years ago? Well, I was actually graduating college. May 9th, 2009 is when I got my chemical engineering degree from the Colorado School of Mines. And as I remembered this coming up on my 10-year anniversary from graduating college, which getting through college itself felt like an eternity, I started feeling a little bit nostalgic. You remember those fluids classes that you took back in school? I was able to go in and dust off my old fluids book here, and I remember them talking about the so-called, simple fluids problems. So here's one of the pages out of my fluids book that talks about these so-called simple solutions to these piping calculations. And I wanted to structure my webinar around one of these old fluids problems that I was able to find. So feeling a little nostalgic, I looked up some textbook fluid problems that used to haunt me. This was a scary one. It's unloading an oil product from a tanker, and this is what the fluids book called a case one type problem, where the flow rate and the diameter. The goal of this example was to calculate what's your pump discharge pressure. And don't lie, I bet some of these fluids problems used to haunt you as well. So I'm not afraid to admit that, and I'm sure that they haunted a lot of us. But now we know how to solve these types of problems. And so this is a solution algorithm for the example that talks about how you would use a spreadsheet in order to calculate the results here. I mean, you can easily do all these calculations by hand, but doing it in a spreadsheet is much easier. So to kick things off with, I just went ahead and reproduced this, and here's the spreadsheet that I created. It's very similar, but just slightly different of a look for what the textbook provided. I've been the type where I actually like to write out very clearly the exact equations that I'm solving, as well as programming them into the cells themselves. So that's part of my OCD. I really like my spreadsheets to look, really quite nice. So this was pretty quick and easy to be able to essentially retype in the same calculations into my spreadsheet that was given in the example. Is there anything that you're able to see that is wrong with my spreadsheet? Well, no, nothing is wrong with my spreadsheet. If you were to go back to the previous slide here, as you can see, the answer for the pump discharge pressure is 132.7 psig. Well, that is exactly what I calculated in my spreadsheet. As you can see, 132.7 psig. There are some things worth noting here, though, with the spreadsheet. Let me go ahead and open it up really quick. I just need to... I thought that I already had it open, but apparently I forgot. Okay. So one of the things is I'm usually really good about stating what the units are, but as you can see, I clearly forgot to state what units I'm using for pressure. So that's one of the things that I would have an issue with. Also, here's another thing is I've got all these conversion factors laid out throughout the spreadsheet here. And the way that I programmed my calculations is if you were to take a look at the flow rate where I converted it from gallons per minute to cubic feet, you can see here that I'm referencing specific cells for those calculations. So if I was to hand this off to somebody, they would have to go in and double check every single calculation in here. They'd have to check the velocity, the Reynolds number, make sure that I've got the right conversions in there, the epsilon over D ratio. And there's a lot of places where things can just go dramatically wrong with the spreadsheet. And that's one of the things that I want to point out. That's one of the issues that there is because everybody is going to have their own different little way of how they put together their spreadsheet, making it very difficult for anyone else to check it. And with all the different calculations that are having to be done, there's so many places where you can easily fat finger a cell and get an incorrect result. So let's go a little bit further with this here. So nothing's wrong with my spreadsheet with the calculations, but I could have made it a little bit more clear on my pressure units, and that's probably about it. So what other questions might we ask for this very simple problem? Again, keep in mind the only thing that the example was asking was what's the pump discharge pressure? Well, what's the elevation at 0.3? There is a second example with this same type of system here. It was a multi-part example, and the third part was to actually calculate how high this intermediate elevation point could be before you started cavitating. And this crude oil that is being modeled from the oil tanker is it has a vapor pressure of 4 psia. So the higher and higher you go, the closer that you'll get to potentially cavitating, and that's what you want to avoid. And there is a solution algorithm in the textbook on how to figure out how high you can go. Other types of questions that you might ask are, what's the MPa stage of the pump? How much pump power is required? If you were to double the flow, how many pumps would be needed? How long would it take to unload the tanker? Will the flow rate actually stay constant? The example assumed a flow rate of 506 gallons per minute. That's what it based all the calculations on. But as this tank begins to drain over time and the storage tank starts to fill, the pump performance is not going to stay at that constant flow rate because your liquid differences are changing. Your static head is going to be changing over time. So your flow rate is not actually going to be constant at 506 gallons per minute.
Yep.
So if you were to start looking at these questions, I bet that you would start feeling a little bit overwhelmed with having to program your spreadsheet to calculate all of those different types of parameters. So there's some thoughts on this oil tanker example that I want to address as well. 506 gallons per minute. How much is that? Well, if you go through the conversions, it's about 17,000 barrels per day. Okay, 17,000 barrels per day. That seems like a lot. Well, how much storage capacity does an oil tanker actually have? And my curiosity got the best of me. So I started doing some research on this to try and learn a little bit more about oil tankers and how much oil they can actually carry. And the answer is lots and lots and lots. It is the second most cost-effective method of delivering petroleum or types of product other than through pipeline. So as I did some research, I found that this is the largest oil tanker built in 1979. Used to be called the Seawise Giant. It was later renamed to the Knock Nevis. How big is that ship? Well, if you were to lay the ship end to end and compare them to the sizes of various buildings, it is very, very close to the second and third largest buildings in the world. That is a incredibly long.
I don't know if I'd say like we're super.
Give me 1 second here.
Like,
okay. All right. So that's a very long ship. Well, how much oil is it possible for that ship to actually carry? I found it was about 4.2 million barrels of crude oil. So the whole 17,000 barrels per day, if you were to try and discharge the tank at a rate of 506 gallons per minute, you're never going to empty that vessel. It's going to be there in port forever. So the reason why I thought that this was interesting is because there's a massive difference between academic examples and reality. So that example that is in the textbook just does not show real life at all with the actual magnitudes that we're dealing with in industry. And so systems are much larger and a lot more complicated than what we were usually taught how to solve. So the whole spreadsheet calculation and hand calculations that we're given are, very simple until you start asking several other questions about the system. And when you start getting into multiple flow paths, control valves, pressure gauges, multiple pumps in parallel, things like that, your spreadsheets are just not going to do the job. They play a very important role in calculations overall, but they're not the right tool for being able to analyze and really have a good understanding of a complex system. So another thing I wanted to highlight is my fluids textbook didn't even mention algorithms on how to solve transient pipe flow calculations. So that spreadsheet and all that algorithm that it went through was simply for just calculating a simple steady state situation. And as we know in reality, things are rarely ever steady state. So how do you handle the complexities of non-steady state behavior? Here are some common transient situations that you might want to examine. Discharging to different liquid heights in tanks. Will any of the tanks drain or overfill in a certain amount of time? If you're filling up a tank with a very corrosive liquid, you definitely don't want it to overfill. That would be a big problem. You can have your valves opening and closing based upon operating conditions. Pumps would change their operating performance based upon your flow demand. You could stumble into operating modes that would not be good, such as flowing far away from your best efficiency point. Maybe you might start cavitating or overpressurizing your system. All significant issues that need to be dealt with, which are simply just not steady state cases at all. So traditionally what people would do is they would handle all of these different transient situations with running multiple steady state cases, different liquid heights, different operating points on a pump, different control valve set points, etc. And they would use that to kind of try and bracket the conditions. Well, that's all fine and good, but it still does not give you a very detailed picture of what's actually going on, because if you were to do it manually, there's just not enough time to be able to see all the different cases that you would need to look at. And so you wouldn't have very good resolution in your results. You might miss important intermediate results. Maybe you have a different combination of liquid heights that results in too high of a pressure in your system. Or maybe your pump drops to a very low BEP proximity. And so if you're not looking at things like that, then you can easily miss it. It also does not handle dynamic interaction between components as your control valves change and your pumps change. So usually they're either ignored or modeled with different iterative runs. So this is where we have AFT Fathom with the extended time simulation module, XTS for short. So again, if you go back to the AFT Fathom product page on our website, this is the module that I'm talking about today, extended time simulation. So if you were to launch that, you'd be able to learn about the different capabilities that are available with doing transient modeling with XTS. So now I'm going to apply this to the oil tanker in Fathom. So here's my system. When I modeled this in Fathom, I built the model just like it was in the textbook. And as you can see here, I did assume a elevation of this high point. So my pump and the pipe are going to be my 0 point. And the liquid level in the storage tank and the tanker is 15 feet. So 15 feet high for a storage tanker tank, that seems fairly reasonable. And then my discharge tank is going to be at a height of 200 feet. So we have to pump over a hill of over 6,000 feet and over a high point of 250 feet there. So this is what I modeled in Fathom. I want to assume a 1 hour simulation period, and over an hour, I'm going to determine, does the oil tanker fully drain within that time frame? So does it take an hour? Does it take 7 hours? Who knows? So I'm going to start by just pumping oil out of the tanker, and I'm going to let it run for an hour and start filling up the storage tank and see what happens. Excuse me. All right. Some other questions that I want to examine. Does the flow rate change over time? What happens to the static head? How does the MPSH margin change? How does the pump's BEP proximity change? The way that I'm modeling each of the tanks, I am assuming a 20-foot diameter tank. So a 20-foot diameter tank would result in about 315 square feet for the cross-sectional area. This is my supply tank in the oil tanker, and this is the storage tank at the top of the hill. As you can see here, I have different liquid heights, and for my storage tank in the tanker, I've modeled it being full at 15 feet high, and you can see I'm using pipe elevation where I've connected the pipe at the bottom of the tank. The reason why it's helpful to use pipe elevation instead of pipe depth is because as your liquid height changes over time, as it goes up and down, if you were to use pipe depth, then your pipe connection would be changing as well, which is not real. So that's why it's more important to use elevation. That way your pipe connection stays fixed. The depth option is a simplistic feature that you can use when you're just doing a steady state operation. The tank on the right-hand side here, this is my storage tank at the top of the hill. So it's 200 feet high. The tank bottom elevation is at 200 feet, and that's where my pipe is connected. And I've got a 30-foot high tank. So as you can see here, the tank is initially empty. There's nothing in it. All right, let me go ahead and jump into Fathom now. The moment that you've all been waiting for. Okay, so getting my oil tanker problem loaded up here. Excellent. Okay, so when I first started building this example, I started off very simply with a pump sizing case. So in my pump sizing simulation, I was doing a steady state scenario. I was not doing transient modeling yet. And so the reason for that is because I don't have a pump curve. So I started off by assuming the fixed flow rate that was given in the example, and I'm using the sizing option to determine a pump curve that will meet my operating conditions. So if we were to run this here in regular steady state mode, we could see what the pump performance looks like. And as you can see, we need 361 feet of head for that pump in order to overcome elevation change and system resistance. If I go to the visual report here, we can see that the pressure at the discharge of my pump, which is right here, is exactly 132.7 psig. Same calculation as the textbook example. Modeling the fluid was very easy. I just simply typed in the density, viscosity, and vapor pressure and called it the 35-degree API crude. That's what the textbook called it. So that was nice and simple. So now after I got my pump curve, which in order to get the pump curve, I used the IntelliClip option for sizing a pump. I'm not going to go through that process right now, but if you were to go to our Learning Center and then video tutorials, you can do a search for Fathom and then narrow this down by technical videos. And this is the video right here that I'm talking about. It's called AFT Fathom Internet Pump Selection. So if you watch that video, it'll show you how you can easily use Fathom to select a pump from a real vendor. That way you can get a real pump curve loaded right into Fathom. So if I go back to the workspace here and I open up my pump, you can see here that for this scenario, I am using a pump curve. So I've got my head curve, my MPSH curve, and my efficiency curve. The pump is operating at its rated speed, 2,500 RPM, and it's just under a 14-inch impeller. Okay, so if we ran this example here, we would be able to compare it to the results of the previous scenario. So if I go into my output control window here, and I turn on my multi-scenario output, we can see how the pump performs in reality with an actual pump curve. So as you can see, based upon looking at the operating points for fixed flow versus a pump curve, the curve is doing an excellent job at meeting my original operating condition. And also, I have much more detailed information about the actual pump efficiency. As you can see, it's about 65%. We know what the power draw is, the proximity to the best efficiency point, and the MPSH margin. So that's a lot of good information that we can gather from that. All right. One other thing that I was curious about is if I needed to apply viscosity corrections. Now, the pump test fluid is typically using water, but I have a viscosity of 13.2 centipoise. So that's a decently high viscosity. I might need to account for the pump correction factors in this system when I'm pumping a more viscous fluid than the pump test fluid. So I went into the pump window here, and on the optional tab, I turned on the calculation to apply viscosity corrections. And that way it'll calculate the correction factors to your flow rate, your pump head, and your efficiency based upon the Hydraulic Institute standards. Now, I'm not going to go through that process, nor am I going to go through the results. The viscosity corrections did not change the actual values very much at all. So I decided I'm going to neglect viscosity corrections for my transient analysis. So if you go to Show Examples under the Help menu in AFT Fathom, and then you pick your favorite units, you can expand the walkthrough examples here. And the walkthrough examples, you can find the crude oil pipeline example. That walkthrough tutorial will teach you about how you can use the viscosity correction calculations. And actually, it looks very similar to the example that I'm modeling here, which it's not exactly the same, but it's similar. All right, give me just 1 second. Okay, apologies for that. It's a very dry climate here in Colorado Springs, and my voice is starting to get kind of scratchy, so had to take a quick few seconds to rehydrate there. but ready to keep trucking along. Okay, so let's look at the transients example now. So for the transient, the first question is, how do you turn on the extended time simulation module? There's multiple ways that you can do it. One way is by clicking on this button that is just to the left of the status light. The other area is from the tools menu. So if I was to click on either of those options, you can see where you can activate the modules and then simply check the box for the module you want to use. If it finds a license that's available for you, then you can use those extended capabilities. For completeness, the other area is if you go to Tools and then Activate Modules, this is the other way that you can activate the modules right in here. So I've turned on my extended time simulation module. I'm ready to do some transient calculations. So the next thing that you would do is under the analysis menu, you go to time simulation. You could simply do steady state only or transient. So let's say that you did a transient simulation, but then you want to go back to doing just a very simple steady state run. You don't have to turn off the add-on module, nor do you have to delete all the transient data that you specified. Simply change it to steady state only, and you can do a simple steady state run. After you turn on transient mode, this transient control will become active. So if I open up the transient control, this is where I define my simulation period. As I mentioned, I want to run the simulation for an hour, and I want to see how much flow is able to be transferred from the tanker to the storage tank. So the way that I did this was I specified a stop time of 60 minutes. You can change the units with the drop-down menus. So if I click on the drop-down menus, you can do different units. I specified a time step of 30 seconds. So I'm going to be doing 30-second data points throughout my hour-long time period. So that's 120 time steps. Now, some of you might be asking, why do you have a start time of 0? Well, the answer is maybe you might be doing a space application when you're launching a rocket. Well, if you have a situation where you have times that are before a certain 0 point, then that's where you can do a non-zero start time. That's probably the only situation where you do that. So if you're doing a rocket launch, T minus 15 seconds, that's where you'd have a start time of perhaps negative 15. All right, so basically that's really all that you need to specify with the transient control there. You can also specify how often you're going to save the output to the file. With doing a transient analysis, the output file could get to be quite large. It might make your model run a little bit longer. So if you skip time steps, it'll run a little bit shorter. I'm not going to do that, so I'm just going to do an hour-long runtime, 30-second time steps. The next thing that I want to do is set up my tanks. So after you turn on XTS, apologies again for that. I had to rehydrate again. Okay, so when you turn on the XTS module, you can see that you have some additional options. There is a finite open tank option and a finite closed tank option. You could use either one of those. If you were to do a finite closed tank, you would have to account for the gas thermodynamics above the liquid surface, and that way, as your liquid height changes in the tank over time, your tank pressure above the gas or inside the gas will also change. So we are accounting for that when you're modeling a closed tank, which it certainly would be if it's on a tanker. But for the case of simplicity of the example and also for my model, I just assumed a finite open tank. So because this is a 20-foot diameter tank, I've got a cross-sectional area of about 315 square feet. My liquid height is going to be 15 feet of liquid above the tank bottom, which is what I'm calling my 0 point here. That's also where my pipe is going to be connected. And my actual tank height is about 5 feet higher. So there's 5 feet of space in that tank that has no liquid in it. So this is one of the simplest transient simulations that you can do with the XTS module. Simply specify a finite tank. I've got a finite tank specified here as well. Same cross-sectional area, liquid height of 200 feet, but my liquid is initially empty. So I'm going to fill it up, and I've got a 30-foot high tank for storage. So this is the simplest transient simulation module where you can do. You just define finite tanks, and then you run your pump. The pump is going to be operating on its curve, and then as the liquid heights change, we're going to be able to see where the pump flow rate is changing over time. So I'm going to go ahead and run my simulation now. And this doesn't take too long for it to run, just a few seconds. All right, so let's take a look at the output now. Let's see here. Those warning messages were surprising me. I was not supposed to see warning messages, but because I was displaying results for other scenarios right here, I just simply had to update my output control to only show the results of my transient scenario. So don't worry about the warning messages that you saw there. Those do not apply to this specific scenario. Okay, so after you run the model, there's tons of information that you can look at. So if you were to look at the pipes and junctions results, these are the results in the pipes and junctions at a certain time step. So as you can see at time 0, that is what my results will be. If you click on the arrows down in the bottom left-hand corner, this is how you can move the scaling tool for the time back and forth. So if I start moving forward, you can see how the results are changing over time. This is only one of the ways that you can examine the results. And this is probably not the easiest way to do it because you're only looking at what the results are at a certain time step throughout your system. Another way is to look at the transient tab. If you look at the transient tab, you have it separated by each of the different pipes. This is pipe number 1. This is pipe number 2. So here's our discharge pipe. Remember how we cared about what the pressure was at the discharge of the pump? Well, that would be this column right here. So if I was to right click on this column, I can choose quick graph, and this will quickly graph the pressure and how it changes over time for that particular column. So this is my pump discharge pressure over time. It starts right at around 137 psig, and then the discharge pressure drops over time. Not significantly, just a little bit. Excuse me. Hang on a second. All right, apologies for that. So that's how your pump discharge pressure changes. Let's go back to those questions again really quick here. We wanted to know, does the oil tanker fully drain? So what we can do there is I'm going to collapse the pipes results, and I'm going to go to the reservoir transient tab. The reservoir transient tab contains the results that change for a reservoir over time. So reservoir number 1, this is my oil tanker, and I've got liquid height in here. So if I right click on the column for liquid height, I can generate a quick graph, and I can see that in an hour, the liquid height almost reaches 0. So at 60 minutes into the simulation, I'm at a liquid height in the supply tank of 2 feet. So based upon the pump that was sized for an initial steady state flow rate of 506 gallons per minute, it's going to take just a little over an hour in order to drain that oil tanker completely. And as you can see with the really large oil tankers, in reality, you're going to need a lot more flow in order to drain those tankers faster. Now, how does the pump operate over time? Well, if I go to the pump transient, I can expand the results for the pump. And as you can see for my quick graph, your pump flow rate actually starts at 526 gallons per minute, and it finishes at just under 500. So the question you might have is, why is the pump at 526 gallons per minute? I thought I said it was 506 gallons per minute. Well, I did, but when I did my pump sizing, based upon the textbook example, which if we go back to the page here, the textbook example does not specify what the liquid height is inside the tank. It assumes that the liquid height here is the same as the pump discharge, which may or may not be true. So because we don't know how much liquid height is inside this example, I made an assumption for my model. So when I did the steady state pump sizing case, I based it off of 0 for the liquid height. As you can see, 0. But then when I did my transient analysis, I did my liquid height at 15 feet. So if we look at this here, it's at 15 feet. That's why we see a little bit more flow there. So this is one of the things that you would not be able to capture easily if you were just doing hand calculations or spreadsheet calculations. All right, what other questions were we asking on this example here? We wanted to know what happens to the static head. Well, as your supply tank is changing, your supply tank liquid height, your storage tank height. So if I go to the graph results, this is the best way to analyze your results, is with graphs. So when you do an XTS simulation, there's a new transient tab that's available. So if I go to the transient tab here, I'm going to choose reservoir, and I'm going to plot the liquid height for the two reservoirs over time. So here we can see how my liquid height in tank 1, which is my oil tanker, you can see how that drains versus how the storage tank increases over time. So what would be the static head change over time? Well, if I simply clicked on copy XY data, and then I went into my spreadsheet, I'm going to go ahead and create another tab. I'm going to paste that data, and then I'm going to I'm going to calculate my static head. There we go. And then if I go ahead and plot this, there we go. So this is how your static head changes over time. And as you can see, it drops off quite a bit. So your static head is changing, your pump flow rate is changing. We might want to be, we want to make sure that we're not going to run into any MPSH issues. So how does the MPSH change over time? Well, one thing that you can do is you can change it to pumps, and you can look at the pump MPSH-A, and maybe you add on the pump MPSHR, and you could stack the graphs together. But there's an easier way, and there's MPSH margin. So let's look at the MPSH margin ratio. This is your MPSHA to your MPSHR. So I want to make sure that this is greater than 1. And it is. So here, if I was to look at the output table, I can look at my MPSHA and my MPSHR. The margin ratio is simply your MPSHA divided by your MPSHR. You want to make sure that stays well above a value of 1. And in my case, it does. So in an hour, I don't have any MPSH issues that I need to worry about for my pump. So that's good. And then the last question, how's the pump BEP proximity change over time? Well, it doesn't change very much. So we start off at a proximity to the best efficiency point of about 90%, and after an hour, it's down to about 80%. So this is not a significant change to worry about in your BEP proximity. You're still well above within the range of 80% to 110%. So this operation here of unloading your tanker is fine, but it's a very small flow rate. It's going to take a really long time to drain that tank, especially when you get to larger and larger tank sizes. Okay, so this is just a very simple situation where I'm simply draining this tank and filling this tank, and that's all that's going on. So now let's take a look back at some of the other complicated examples that the textbook had. So this is another example of a complicated, I use that in quotes, because if you're doing this by hand or with an Excel spreadsheet, this would be a very complicated system. But when you have a software tool like Fathom, especially with the XTS module, this becomes child's play, because the algorithms that this example lays out in the textbook on how to solve this problem using Newton-Raphson methods for doing the flow balance calculations, that's all this is calculating. It's only determining what your overall flow rates are in each of the pipes as well as the overall pressures. You don't get to calculate any other information. With this spreadsheet, you'd have to add on your own additional parameters. So when you have a software tool, this becomes child's play. Keep in mind that, again, the fluids books, they commonly do not talk about how to do a transient analysis. And so this is a complicated system only based upon a steady state operation, where in reality, it's not going to be steady. This tank is going to drain. These two tanks are going to fill, and they're going to fill up at different rates potentially. So moral of the story is these complex systems are easy to analyze and understand with the flow analysis tool, difficult to impossible with hand calculations or spreadsheets. So let's fill up some more tanks. I have a system that I'm going to model here where I have 3 different discharge tanks. They are all at different elevations. So I've got a tank at a 400-foot elevation, 275, 200. I've got different diameter piping, 6-inch, 4-inch, 4-inch. I've got different lengths. If you take a look at the lengths, I've got 1,600 feet, 2,000 feet, and 2,300 feet. And so that's how I'm modeling my system. These are the steady state results based upon my original design flow rate was 1,000 gallons per minute. So I specified a fixed flow rate of 1,000 gallons per minute, and then I used the IntelliClip feature to size my pump. So this 1,005, that's based upon a real pump curve that's built into the model. So let me go ahead and open up this example here. The questions I want to ask: how long does it take to fill each of the tanks? Do any of them overfill? How does the pump operation change? So let me go ahead and open up that model here. All right. So again, my base scenario, I was doing my pump sizing calculation, and I'm not going to go through that. It was virtually the same thing that I did for the oil tanker. So now I want to get into my transient analysis. So here's my very first transient case that I did, tank filling. So I turned on my XTS module, and the simulation period that I want to run this model for is for 2 hours. So I've got a 2-hour simulation period, and I'm taking data at every 30-second time steps. All right. So after I went through and I specified that, I actually went ahead and I included some valves in this piping system as well. So I didn't have the valves in my screenshot, but I put them in later, and you'll see why in a minute. So right now, if I don't do anything to those valves, they just stay completely wide open. I have my tanks defined with different geometries. So my supply tank here is based upon a 40-foot diameter, and I've got a 50-foot liquid height supply tank. So that's a pretty large supply tank there. And then for each of these other tanks, I've got a diameter, or this is based upon a 20-foot diameter, 30-foot high tank. This tank is 10 feet in diameter, 20 feet high, and this tank here is 30 feet in diameter, 10 foot high. So after I went through and I defined those as finite tanks, I didn't define any other transient information. I just want to see, how do these liquid heights change over time? So I'm going to go ahead and run my transient simulation. Now, one of the questions that's important of being able to determine when you want to see how your supply tanks or your tanks change over time is, do any of them overfill? Because if they overfill, then that's a major problem. So let's take a look at the results here. If I go to the output window, it would display if I have any caution messages or warnings, but in this case, I don't. No warnings, and I've got results. If I show the results for the pump, you can see how the pump flow rate changes over that 2-hour period. So we start off at about 1,000 gallons per minute, and after 2 hours, we're almost down to about 870 gallons per minute. That takes a pretty significant toll on the percentage proximity of the BEP. So if I do the BEP proximity and quick graph that, you can see that when I sized my pump, we started off really high. So at 1,000 gallons per minute, I'm at 98% of the best efficiency point. But by the time that the 2-hour period is over, I'm down to about 85%, which in this particular example is not a huge issue. But the question is there any problem with the model here? Or is there any problem with the system? Well, this is where, when you're doing a transient analysis, you've got to look at things a little bit deeper, because it's not clear just by looking at these results in these tables. So what I've done is, on the graph results tab, I went into the transient tab here and I selected reservoir, and I am plotting the liquid heights for each of these reservoirs. I've already done that, so I don't have to reset these parameters. All I need to do is come in and double click on this graph list item, and here we go. So these are my liquid heights for all of my tanks. The red line, this is my supply tank here, so you can see how that changes. And then look at this yellow line. The yellow line increases, and then all of a sudden it levels off. What's going on there? Well, if you look at the liquid level 20 feet, it stays exactly at 20 feet for the whole rest of the simulation. So what's happening is, in tank 5, I have reached my 20-foot limit. So this is a major problem, because if I don't shut off the flow to that tank, then it's going to overfill for the whole rest of this period. So if we were to go in and take a deeper look at this, I could see that my tank starts to overfill 35 minutes, and then for the next 90 minutes or so, I'm just losing a whole bunch of product. And that's a terrible, terrible thing that you don't want to have happen. So how can we prevent that? Well, that's why I put the valves in. So this is my scenario where I have specified a transient on each of these valves. What I want to have happen is I want each of these valves to close when any of these tanks happen to get very close to overfilling. So if I open up the valves here, I've got a new component in the system that can cause the transient results to change. So here I'm using a standard handbook loss model for a ball valve where I have my K factor calculated based upon that loss model. And when I went to the transient tab, there's 4 different types of transients. There's a time transient, single event, dual event, etc. I'm not going to get into all the complexities of the different types of transients. What I'm doing here is a simple single event transient. So I want this valve to close before my tank overfills. I do not want the cup to runneth over. So my event type that I've selected is reservoir liquid height, and once the reservoir liquid height gets to be greater than or equal to 28 feet for this specific tank, J4, I'm going to close the valve in this profile here. So the reason why this is a single event is because in order for this valve to actually close, this criteria has to be met. So what I'm saying here is if the liquid height inside this tank never gets to be 28 feet during that 2-hour time frame, then this valve will never close. It'll only close once that criteria is met. And here, I'm closing the valve over a period of 30 seconds. Now, this is something I want to highlight that is different between the AFT Fathom XTS module and what AFT Impulse does for Waterhammer. I will highlight this again in the next webinar that I do here in the next few weeks. So to give you a little prelude of that is when I close this valve, I'm assuming that after this 30-second time period, the next time step, which is 30 seconds away, I'm assuming that any pressure waves that have been propagated through the system due to that valve closure have fully dampened out. That way, at my next time step, I essentially would be at a steady state. So Fathom is not going to capture how the pressure surge passes through your system at thousands of feet per second when you have a sudden change like this. So it's going to assume steady state behavior, and it's going to ignore the wave speed of the fluid, and it's not going to know how fast those waves pass through the system. That's what you will need Impulse for. And again, I'll go into more detail on that in one of the next webinars in the next few weeks here, so make sure that you register for that. All right, this valve here, instead of closing at 28 feet, since this tank is only 20 feet high, I want it to close at 18 feet for J5. And then the last tank, I want it to close when it's 9 feet. So when this tank, which actually has a fairly large diameter of 30 feet, it's a pretty large tank there, 9 feet, I've still got a little bit more room. So that's why I did just 1 foot below the liquid surface rather than 2 feet, because with a huge diameter tank, I've got a little bit more margin there. I can accommodate a little bit more flow. So with this being my new system, when do those valves close? Do any of them close? Once they close, how does the flow distribution change? All right, so let's run the model. So I'm running the model here, and the thing that we'll be able to look at first is when do the valves close? And when we take a look at the output window, there's a couple of new tabs that might occur called event messages. And we'll see that right now. So if I go to the output window here, there's some event messages tabs. Let's go back to the workspace really quick before I go on to that. If I go back to the workspace, you can see how all of a sudden these two pipelines are dotted. What this represents is the final steady state, or I'm sorry, the final result. The final result is where these two flow paths are actually turned off. So at some point, those valves closed. I have no flow in those pipes at some point anymore. But this does not tell you when. You have to look deeper. So if I go to the output window, I can see that I have two new tabs in my general section. Event messages by junction and event messages by time. Let's look at event messages by time so that it shows things chronologically. So if I look at my event messages by time, I can see that my first valve closes at 32 minutes, and then my second valve closes at 113 minutes. So what that's telling me is if I go back to the workspace, this valve closes pretty quickly early into the simulation, and then this closes a little bit later. So we're going to be able to monitor how the flow distribution changes during that process. But before, let's take a look at the pump flow rate over time. So I go to the pump transient. If you remember from before, I went from 1,000 gallons per minute down to about 870 or so. Well, when those two valves close, that's closing off flow to the system. So at the very end of the simulation, I'm not operating at 870 anymore. I'm operating way down below 500 gallons per minute. What does that look like on the proximity to the BEP? Well, it's severe. So when the first valve closes right here, we have a sudden drop in the proximity to the best efficiency point. And until that second valve closes, we're still above 70% of the BEP. So that's not bad. But once those two valves close and you're only flowing to one of the tanks, look at this. You're now down to about 45% of your BEP. That's not good, and you may not be able to sustain that for a very long time. So certainly something you would want to be aware of. So if I go to my graph results window again, I can double click on my liquid height graph list item. Let me try that again. There we go. And look at this. You can see how your yellow line, it becomes 18 feet. So here, we're not overfilling the tank because that valve is closed. So this is good. My valve is closing at that time. What you can see here is a very slight change in the slope for the other tanks here. So when this valve closes, it starts diverting that difference in flow to the other two tanks, and that's why we have a slight change in slope. If we go out later in the simulation here, to this point, this is when my second valve closes, and now you can see how there's another change in slope where all the flow is going to the final discharge tank. There's one more thing I want to plot here. I want to see how the flow rate changes to each of those tanks over time. So what I can do here is I can click on valves, and I'm going to show the volumetric flow rate through each of the valves. All right, let's look at these one at a time. So here's my valve that leads to the first tank. So if I dock this over to the side, collapse that panel, and then go back to the workspace, this valve J8 is this tank right here. So you can see how the flow rate changes into that tank, and then it increases, and then it increases again. Then we can take a look at the middle valve, so you can see how that flow shuts off almost immediately. And finally, the last valve, when the first valve shuts off, you have a little bit of a spike in additional flow, and then all of a sudden that drops off once the valve is closed there. And at that point, that's when all the flow is going through J8. All right, so that is the XTS module. And what I've shown you here is how you can easily calculate the reality of a system like this by using the XTS module, where there's no longer a need for doing spreadsheets. Yes, you could do high and low liquid tank heights, which would be assumed to be infinite reservoirs, to see how your pump would change, but you're going to completely miss when these valves close during the overall process. And you're not going to be able to get a good idea of what the actual flow distribution would be, nor would you know how your flow rate through the pump changes over time. So rather than doing a whole bunch of separate steady state runs and throwing those aggregate results into Excel, just use the XTS module and you'll make it so much easier on yourself. And XTS will capture exactly what's going to be happening throughout your system during that simulation period. And then I also talked about how you can do different transients on components. And so based upon a single event transient, in order for this valve to change position, it required a certain criteria. And so that's what an event transient is. All right, thank you all very much for your time today. Definitely be sure to register for our next upcoming webinars. So if you go to our website to upcoming webinars, the next one that we're going to be doing is coming up on May 15th, 2 weeks from today. What does transient analysis really mean? So now that we saw the very basic capabilities of what XTS does, I'm going to go into more detail about the differences in a transient simulation using the Fathom XTS module, and how the transient analysis is different for AFT Impulse with WaterHammer. So when you use the word transient analysis, it means different things. It depends on what you're talking about, short-term or long-term. And we'll be able to see what different types of questions you would ask for the XTS module versus what you would use Impulse for. So be sure to register for that webinar if you haven't already, and I'll look forward to seeing you all in a couple of weeks. If anyone has any questions, feel free to contact us at sales@aft.com, or if you have tech support related questions, you can send them to support@aft.com. If you don't have access to the XTS module and you want to try it out for a little bit, contact me and I'll be happy to set that up for you. My email is benkeiser@aft.com. Thank you very much, everyone. Take care and have a wonderful rest of your week.